Push a 10 kilogram block up a ramp using a constant horizontal force for each distance of 5 meters. The box gains 4 meters in height. And so on. So, just right off the bat, because I'll probably need it, I'm going to calculate this angle. Sine of theta is going to be 4/5. That means theta is inverse sine of 4/5. Inverse sine, or 4/5 inverse sine 53.13 degrees. Find the work done by the force F. For each 5 meters, the box moves parallel to the ramp surface. So here's the box. There's a force, an applied force F. It has magnitude 300 newtons. There's a normal force, N. There's gravity down. But in part A, we're not asked about the work done by any of those forces, just by the work done by F. So let's go into the angled coordinate system. And I'll differentiate the rotated coordinate system by the use of primes. The positive x prime direction points up the incline, and so if I draw this horizontal line, this angle is the same angle as the incline, and I want to get projections of the force F onto the x and y prime coordinates. So let me go into a different color. So here's F, this force. So I've got a component, something bright. I've got a component in this direction and a component in this direction. So F, the vector F, is going to be the magnitude of F times cosine theta in the I hat direction. I use primes because we're talking about the rotated coordinate system. Negative magnitude of F sine theta j hat prime. The displacement that we're talking about in this case is only 5 meters. So I'll just put 5 meters, and in the x prime direction. So the work done by the applied force is just F dot S, and that is F cosine theta I hat prime. I'll write it out and do it all official, even though I know this component, this term, doesn't enter into the calculation. That's an I hat. Alright, F is the magnitude, 300 newtons. And theta was 53.13, so this is 5 times 300. I'm going to leave off the sig figs and units for a minute. Times cosine theta I hat dot I hat minus sine theta j hat dot I hat with the primes. And this term is 0 because j dot I is 0. J and I are orthogonal. And then here, this just becomes 1. So, what is that? 1500 cosine 53.13 degrees. So cosine of that times 1500, 900 Newton meters, or 900 joules. The ramp is made of rollers and can be considered frictionless. What is the maximum mass of the box that your force F can move up the ramp? Alright, so we weren't given a mass. However, if we look at the forces acting on the box again, so that's, or the block, whatever. We've got an applied force this way, a normal force this way. If there were friction, it would act in this direction, but no friction. We do have gravity acting, that's downwards. Alright, so how do we do this? What is the maximum mass of the box that your force F can move up the ramp? I'm going to put in a dotted line the direction of up the ramp. So that would have been angle theta. How do we do it? Okay. That should be 90 degrees. It's just a sketch. What we need... So the key words here, move up the ramp. Alright, so in our rotated coordinate system, we need a net or a total force. It's going to be the normal force plus the applied force plus gravity, all added vectorially. These are vector signs. This app isn't as nice as the other app I was using, but the PDF background is better in this app. Anyway, this is just a definition of a total force. The Newton's second law part is setting the total force equal to the mass times the acceleration. And in particular, this is the mass times a x prime in the I hat direction plus a y prime in the j hat prime direction. If this term is greater than 0, then the box, let me make a little illustration, then the box will slide and accelerate up the incline. If ax prime is less than 0, that means a negative acceleration in the x direction, so it slides. Not only does it slide down the box, but it accelerates down the box. However, if ax prime were 0, then this force could either go up or down the box, but it would move at a constant speed, constant velocity. So it's something about, this question is asking something about the total force in the x prime direction. Let me just put the y prime direction also on here just for consistency. But we're looking at this guy. Get rid of that. So let's add up all these forces and then look at the x component, or the I prime component. So n is just n j hat f. We found above this guy, so I'll go ahead and copy and paste it. I'll even make it change color. Let me also move it so it doesn't interfere with what we have. Okay. And W, that's another one that's a little bit tricky. So that points straight down, and I want to get the projections onto x and y prime. And this theta, oops, let's see. So as theta goes to 0, this component of y, the gravitational vector, goes to 0. Or gets smaller and smaller until it goes to 0, right? That means this angle must be theta. So W cosine W sine theta I hat prime negative, because it's in the negative x prime direction. And then negative W cosine theta j hat prime. So adding all these forces together, I get F total equaling F cosine theta minus W sine theta I hat plus N minus F sine theta minus W cosine theta j hat. And it is going to add a page so I can move this up. It's this component that we're examining, because we want that to be 0. If this thing is greater than 0, then the block accelerates up the incline. If it's less than 0, then it accelerates down the incline. If it's equal 0, then there's still a chance that the block can go up. I mean, it could still go down, but we can still have it go up. So that'll be the key. F cosine theta minus W sine theta equals 0, which means F cosine theta equals W sine theta. This W is weight, right? Not the work. I think I've been trying to consistently write a more italicized W for the work, and then a blockier W for the weight. And the weight, as usual, is just mg sine theta, and therefore, solving for m, F cosine theta divided by g sine theta. And because we like to simplify, this is, what is this? G cotangent theta. Cotangent is just 1 over tangent. So, M equals, what was it, 300? Yeah, 300 newtons divided by 9.8 meters per second squared times cotangent. You know what? I don't have a cotangent button on my calculator, so I'll just do 1 over tangent of, was it 53.13? Was it? Yeah. So 300 divided by 9.8 divided by 53.13 tangent equals, I get 22.959. So 23.0 kilograms. So if the mass was any more than this, then this wouldn't be equality. This would be greater, which means this would be negative, which means the total force in the x direction would be negative, which means the block would slide or accelerate down the incline. And it's the opposite if m were smaller than this, 23 kilograms. If m were smaller, then we'd have well, not this one, but this f cosine theta would be greater than w sine theta, which means this is positive, which means f total x prime is greater than 0. So that the total force in the x prime direction would be positive, which means the block would slide or accelerate up the incline. It's right in the middle, right? Right when m is about 23 kilograms is when all these forces balance. So the total force in the x prime direction is 0, which means there's a chance for the block to just go up the incline but not accelerate, just have a constant velocity up the incline. That's the magic concept to this problem.